The lecture today is going to talk about electric fields, electric charge. And so the first thing that we want to talk about is what is a field? Now, how do we think about a field? Now, any quantity that depends on where you are in space, in location, can be represented by a mathematical object that we call a field. So, for example, if you go to the weather website and ask for a map of the temperature of the US, you might get the map above here. And it shows you for every point in the US what the temperature is. In fact, it shows you a number here, but also a color code at the top so you can see the fine gradations of change as you go from one place to another. It gets warmer or cooler across the US. And likewise, you could get a map of the wind speed as a function of position in the US. And you can see on this particular day that I chose this, in the upper Midwest, there was quite a lot of wind, 30 miles an hour in Minnesota there. So they must have been having storms. But now, remember that wind is a little different from temperature, right? It has not only a speed, but a direction in space. So we really should be representing the wind by vectors. And here's a picture of the winds over the oceans on the Earth. We could have done it for the US too. In this case, you have a vector quantity, the wind velocity, which depends on position on the Earth's surface. Now that's something that we can represent by a mathematical object we call a vector field. It's a field because it depends on where you are in space, and because the thing that you're representing is a vector, it's a vector field. All right? It's a really pretty straightforward concept with a scary-looking name like a vector field. Okay? And it has an even scarier-looking mathematical representation. When you write it out, you could say, well, the wind velocity, which is a vector, depends on your position, x and y. And it has a component v sub x, which depends on x and y in the x hat direction, plus a component in the y direction, v sub y, which also depends on where you are, x and y, in the y hat direction. That's what this complicated looking thing means. You go, oh my gosh, it looks like v times x and v times y. It's kind of hard when you look at that to decipher it in one glance. But these are just functions. These components themselves are actually scalar fields themselves. So you can represent a vector field by the component scalar fields and just give them directions in the x direction, the y direction, z direction. Well, we go through all this because that's what we're going to do with electric fields. But before we get there, let's do a clicker question and ask the following. Which of the following four things is represented by a vector field? A, the population density of a country. B, the ground level air pressure in the US. C, the acceleration of gravity near the moon's surface. Or D, solar surface temperature. Only one of these things is represented by a vector field. You can talk to each other, of course.